Hi everyone, I am Vignesh V. Menon, a PhD research scholar in Christian Doppler Laboratory, Athena, in University of Klagenfurt, Austria. Welcome to the presentation of the paper titled Perceptually-aware per-title encoding for adaptive video streaming. In this presentation, first I will introduce the basics of per-title encoding, then I will explain the proposed PPTE scheme. Finally, I will explain the results and then conclude this presentation. In live streaming applications, fixed set of bitrate resolution pairs known as bitrate ladder is used for simplicity and efficiency to avoid additional encoding runtime required to find optimum resolution bitrate pairs for every video content. However, an optimized bitrate ladder may result in decreased storage or delivery cost and increased quality of experience. As shown in this figure, for DOL sequence, the crossover bitrate between 540 and 1080p happens at approximately 0.8 Mbps, whereas for PARC sequence, 1080p always remains superior at the entire bitrate range, which means 1080p should be selected for bitrate ladder for the entire bitrate range. This content dependency to select optimal bitrate resolution pairs is the basis of introducing per-title encoding scheme. The selection of bitrate resolution pairs from the convex hull is a very challenging task. The increased number of selected bitrate resolution pairs for the bitrate ladder may improve quality of experience since clients are served with representations close to their desired bitrate range. However, this leads to an increase in storage and bandwidth requirements. For example, as shown in this figure, the selected resolution bitrate pairs and VMAF scores for characters sequences using HLS bitrate are shown. It is observed that there are multiple representations with the same video quality, that is VMAF close to 100. There are also multiple representations with similar quality at mid-range bitrates. Selecting representations with similar quality for the bitrate ladder does not result in improved quality of experience, but it leads to increased storage and bandwidth cost. To mitigate this problem, this paper targets and content adaptive JND-aware online bitrate ladder prediction. As shown in this figure, each point of the bitrate ladder is having a perceptual quality difference of 1 JND. Please note that in this paper, JND is considered as a function of VMAF. This encoding scheme increases the overall compression efficiency of the bitrate ladder encoding, but also decreases the overall storage required to store the representation. The proposed PPTE scheme architecture is shown in this figure. The bitrate ladder is predicted using the spatial and temporal features of the segment and set of predefined resolutions, maximum and minimum target bitrates, average JND, quality function of the bitrate ladder, and maximum VMAF of the bitrate ladder. The minimum bitrate, maximum bitrate, and maximum VMAF are input to the scheme to ensure that the predicted bitrates and VMAF values are within the specified range of bitrates and VMAF values required by the streaming service provider. This ensures that the scheme can be tuned to accommodate the optimized number of representations in the bitrate ladder by considering the maximum bitrate and VMAF supported in the bitrate ladder of streaming service provider. In the online prediction of encoding parameters, selecting low complexity features is critical to ensure low latency video streaming without disruptions. In a video segment, two features, that is average texture energy and average gradient of texture energy, are calculated. A DCT energy-based energy function is used to determine the block-wise texture of each frame as shown in the equation here. The texture is averaged to determine the spatial energy feature denoted as E as shown in the equation here. Furthermore, block-wise sum of absolute difference of the texture energy of each frame compared to its previous frame is computed and then averaged for each frame of the segment to obtain the average temporal energy H as shown in the equation here. Please note that the speed of extracting these features is 370 frames per second for UHD video using 8 CPU threads with x86 SIMD optimization. Now, to determine the first point of the bitrate ladder, the VMAF is predicted for the minimum bitrate, that is Bmin, for all resolutions in the set R as shown in the equation. Here, A0R and A1R are the constants defined for each resolution R. Linear regression is used to determine these constants for every resolution. For VRB0, the values obtained for multiple resolutions, the maximum value is considered for the bitrate ladder. The value of R corresponding to the maximum value is chosen as R0 for the bitrate B0. Thus, R0 B0 is the first point of the bitrate ladder. For every T+1 point of the bitrate ladder of the target VMAF, we expect target VMAF is the sum of the previous VMAF plus the one JND. The target bitrate of every resolution R to achieve VMAF VT, that is BRVT, is determined as shown in the equation here. From BRVT values obtained for multiple resolutions, the minimum bitrate is considered as the BT for the bitrate ladder. The value of R corresponding to the minimum bitrate is chosen as RT. Thus, RT-BT is determined as the predicted bitrate resolution. This process is done iteratively until the BT is greater than or equal to Bmax, or if VT is greater than or equal to the maximum VMAF. Coming to the results of the proposed scheme, this figure shows the rate distortion curves of encodings of certain test sequences using HLS leader and the proposed scheme. It is observed that the proposed scheme yields higher or the same VMAF as compared to the HLS bitrate ladder encodings at the same target bitrates. Additionally, the proposed scheme determines RD points such that the average difference between the VMAFs of consecutive RD points is the input JND value. This figure shows the storage reduction results of the test sequences with the corresponding spatial and temporal complexity values. It is observed that highest storage reduction is observed for medium complexity videos. As shown in this, the second figure, it shows the John-Gard delta rays with respect to VMAF for different set of videos. And it is observed that the highest BDR is observed for videos with medium spatial complexity, similar to the storage reduction results. This table summarizes the John-Gard delta rate results with respect to PSNR, VMAF, and the storage reduction results for various test sequences using the proposed scheme. On average, the BDRV and BDRP results of the proposed scheme compared to the HLS bitrate ladder encoding are minus 27.02% and minus 16.47% respectively. And also we have a storage reduction of minus 30.69%. To conclude, this paper proposed a perceptually aware online particle encoding scheme for live streaming applications. The proposed scheme includes an algorithm that predicts the optimal resolution bitrate pairs of every video segment based on JND in visual quality perception. It is observed that live streaming using the proposed scheme requires 16.47 bits to maintain the same PSNR and 27.02% fewer bits to maintain the same VMAF compared to the reference HLS bitrate ladder. The improvement in the compression efficiency achieved with an average storage reduction of 30.69% compared to the reference HLS bitrate ladder. Thank you for attention. Now I will be happy to answer any questions. Thank you.